Alright, I wanted to give a quick mini lecture in this video on polarity and the idea of polarity, where it comes from, what equates to a molecule having polarity, and how do we figure that out. And a lot of it comes from molecular geometry, electronegativity, which we've already discussed, and the behaviors of certain elements when they are in bonding situations. A lot of it comes from the periodic table. So let's take a quick look. The periodic table in your reference material is shown here. I've zoomed in to the part that matters, and it is very important to realize that these numbers at the top of the periodic table on each column, these numbers tell us the number of valence electrons in a element in that column. Remember, that's what these numbers are for. Carbon is 4 valence electrons, nitrogen 5 valence electrons. Why is this important? Because you need the valence electrons to be able to draw the proper Lewis structure, to be able to get the proper molecular geometry, to be able to determine polarity. Remember that. Just remember that. Okay. So here I have a couple of examples of molecular compounds, specifically covalent compounds that involve a metal and a non-metal. I've tried to get a good mixture of ones, some with no double bonds, some with double bonds, some with resonance, some with charge, polar and non-polar. What I'm going to do for each of these is I'm going to go through first drawing the proper Lewis structure. Then we'll go back through and talk about polarity as a function of electronegativity, as a function of position on periodic table. Then we will go and decide whether it is a polar molecule or not, based upon whether it has a net dipole or not. So let's start here. And just to use this as a good nomenclature practice, two nonmetals, this is where we use the name of the first element and then the prefix for the amount of atoms in the second element, and this will be silicon dioxide. It's always good to get nomenclature practice in, even while you're doing molecular geometry. All right, valence electrons. We go to our periodic table, we see that silicon is in the 4A column. That means that it brings 4 to the table. Oxygen brings 6 apiece. So there are 16 valence electrons in this molecule. We need to make sure we use all of those up. Remember, the least electronegative, or generally the one that's on the left, is going to be our central atom. That means that we draw silicon here, and what do we do first? We create a single bond to each of the remaining atoms in the compound. We have now used all of the atoms in the compound, and we have used 4 electrons. That leaves us with a total of 12 electrons. Remember, these electrons go around the most electronegative atom until octet is fulfilled. We put them in pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have no more electrons to add. At this point, anything that we do, if we need to go any further, it has to be done with the electrons that we have available already on the structure. Now, the next thing we do to check and see if we're already done, because we could potentially be done, we check and see if octet is fulfilled on every atom. And we see that that is not the case. We see that that is not the case. Silicon only has 4 electrons associated with it, the 2 bonding pairs. So we must take electrons from an atom that is not the central atom, that has lone pairs, and create a double bond. That creates this structure. we notice that this still does not have silicon with the octet fulfilled. So the last structure, we take an electron pair from that oxygen, and now we have octet fulfilled on all molecules. This is the correct answer. We do not have formal charge. Silicon normally has 4. It's bringing 4 to the ball game. Oxygen normally has 6. It's bringing 6. From a molecular geometry standpoint, this would be considered linear. This would be considered linear. Okay, let's take a look at this molecule. Nomenclature: nitrogen trifluoride. Again, covalent, we go with element to the left, name, then prefix, fluoride. IDE. Suffix on that word for the second element, IDE, always. Nitrogen brings 5 valence electrons, fluorine brings 7. 7, 14, 21, and 5 is 26. We got 26 electrons that we got to deal with. Nitrogen is the least electronegative. Nitrogen belongs in the center. We need to make a bond to each of the fluorines. We have used 6 electrons. That means that we have 20 left. Those 20 go around the most electronegative atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have fulfilled octet. We have used 18. We have 2 left, but we have not fulfilled octet on nitrogen. A lot of people make a mistake here and say, oh, make a double bond. You have jumped the gun. You have jumped the gun in the order in which you need to evaluate the structure. Once you evaluate that nitrogen is missing enough electrons for octet and you have some left, you use lone pairs first. Always use lone pairs before. If you have them left, -2 leaves us with 0 electrons left. If we evaluate this structure, everybody's happy, everybody has octet fulfilled, and this is it. This is the correct structure. Okay, this is the correct structure. Molecular geometry, trigonal pyramidal. Again, these are on your reference materials. Remember your VSEPR chart. You will have those for your exams. All right, let's look at SCO2. Sulfur dichloride. And if we look, we see that sulfur is the least electronegative. It belongs in the middle. Calculation of valence electrons, we have 6 plus 7 plus 7 equals 20. If we make bonds to each of the chlorines, we have used 4. That leaves us with 16. We need lone pairs around the most electronegative. That uses up 12. That leaves us with 4. We do not have octet fulfilled on the sulfur. We add those lone pairs on sulfur to get rid of those 4. And now we have octet fulfilled on all atoms. Structure done. Molecular geometry, if you go to your VSEPR chart, 2 bonds, 2 lone pairs. The mistake most people make here is they write linear. This is bent. This is bent. Sulfur dichloride, bent. All right, and now we get to carbonate. If we go on our reference material, specifically on the back of our periodic table, you will find the polyatomic ions. These are ions, not ionic compounds. These are ions, but they are covalent molecules because we have 2 nonmetals. If we look at the valence electrons here, remember, we have to take into consideration this charge. So we need 4 plus 6 plus 6 plus 6 plus 2, which gives us 10, 16, 22, 24. All right, we want carbon in the middle. We have 3 oxygens around it. That means we've used 6. That leaves us with 18. If we put electrons around the most electronegative, 6, 12, 18, we have used them all. But notice, we have not fulfilled octet on carbon. What must we do? We must create a double bond. Does not matter which oxygen you create that double bond from. That will give you this, that will give you this structure. Octet is fulfilled. Now, specifically because you have the charge, this is a polyatomic ion, you need to evaluate which one of your atoms, if any, have a formal charge, and oxygen has a formal charge on each of these. And again, that comes from, remember, formal charge is equal to Lewis structure minus, ground state minus Lewis structure. And for these 2 particular oxygens, the ground state is 6, but the Lewis structure gives us 7. So therefore, our formal charge is equal to -1. And that's where these charges come from. This is the complete Lewis structure for carbonate. And if we look at our VSEPR chart, 3 things around a central atom without any lone pairs is trigonal planar. All right, so here is a step-by-step demonstration of 4 covalent compounds, 4 different molecular geometries, done start to finish. Should be no excuse whatsoever for any questions about Lewis structures. You need to be able to knock these out of the park. All right, I'm going to erase this and put all 4 of these back up, their structures back up, and then we're going to talk a little bit about their polarity. Okay, here are our 4 molecules that we have just drawn. Now I want to talk a little bit about how polarity impacts these electronegativity and dipoles. Remember, these bonding electrons that are shared between any of the atoms are pulled to one side or the other as a function of electronegativity, which is kind of like greediness. And remember, our transfer electronegativity, they increase as you go up and over. So if we use that situation to determine which one is the more electronegative atom in this molecule, we will know that the more electronegative atom is oxygen. What that means is that our dipole, as it pertains to oxygen, will be in oxygen's direction. Remember, our dipole is an arrow with a plus on the other end. That same dipole has to exist for both oxygens, and the magnitude or the strength of that pull is going to be exactly the same. Because of that, these dipoles cancel, due to linear geometry, and we have a non-polar molecule. Non-polar because of that. Okay, if we take a look at carbonate, if we use the trend of electronegativity increasing up and to the right, we see that oxygen is further to the right than carbon. So oxygen is again, more electronegative. And oxygen will have the dipoles in its direction, these vectors. If we look at the molecular geometry, we end up with the exact same situation, except it's due to trigonal planar. The dipole cancels. Because the dipole cancels in this case, nonpolar. You could also utilize your reference material. If you notice on the back of the periodic table, on the VSEPR chart, it talks about which geometries have nonpolar molecules if every atom around the central atom is the same. Again, the magnitude here is the same, and the magnitude here is all the same, so the pools are equal, they cancel out, nonpolar. Let's take a look over here on this side. On this side, we end up with our this should be NF3. Got ahead of myself. And nitrogen trifluoride, if we look at our trends, we see fluorine is the more electronegative atom. Therefore, the dipole is going to exist towards the fluorine. And if we look at the molecular geometry of nitrogen trifluoride, we remember that it is trigonal pyramidal. And therefore, we do not have cancellation of these three dipoles. It is very different from trigonal planar. Again, remember, trigonal planar is flat. They're all 120 degrees from one another. Trigonal pyramidal sits like a triangular pyramid. So, because of that, we have a net dipole here in this direction. And because we have a net dipole, this molecule is polar. This molecule is polar. Okay. Sulfur dichloride. If we take a look at the electronegativity difference further to the right, chloride is more electronegative. Therefore, the dipole exists towards chloride. Based on its geometry, remember this is bent. Bent geometry is like this. Therefore, there is no cancellation. It's very different than linear. Linear is two in a line. So the magnitude of these are the same, but they are in this setup and that direction. So the net dipole in this case is going to be down. And because we have a net dipole, this molecule is also polar. Now, just to give you some, show you what that really looks like on your reference material, on the VSEPR chart, let's take a quick look at the VSEPR chart. And if we zoom in on the VSEPR chart at the bottom here, it tells us that molecules with this shape are nonpolar when all of the atoms connected to the central atom are the same. If the atoms connected to the central atom are different from each other, the molecule needs to be considered on a case-by-case basis. So whenever you see the little 4 under polarity, if you have got the correct shape, then your polarity can kind of be told to you based on this rule if you have drawn it correctly. But you still need to be able to understand it from this perspective, understanding the dipole and the net dipole as a function of electronegativity. And I hope this helps everybody out. If you got any more questions, feel free to send me an email.